Hello and welcome to this lecture. In this lecture, we are going to start looking at eigenvectors for triangular matrices. In the previous one, we saw for diagonal matrices, eigenvalues and eigenvectors are really easy to write down. Let us push towards triangular matrices. What happens when you have say an upper triangular matrix, not just the diagonal, something above it is non-zero. In that case, what happens? That is what we are going to see. We already saw eigenvalues. Eigenvalues continue to be the values on the diagonal. What happens to eigenvectors? It turns out it changes a little bit. So, you will see what changes when we see some simple examples. Okay. So, let us begin with examples. I am going to start primarily with examples and then illustrate the ideas and then sort of generalize later. Okay. Let us begin with this simple case. We had the 1, 2, 3 diagonal matrix, right. On top of that, in the next diagonal, I am going to add a 1, 1, okay, just to make it triangular. See what happens here. So, let us begin with lambda equals 1. I am going to do a minus I. Okay. So, once again I am going to subtract 1 from the diagonal. So, you have got a 0 0 0, right, you have got a 0 0 0 column, okay, something is there on the other side, but you quickly observe rank is 2, nullity is 1, geometric multiplicity is 1. Okay. So, you have got lambda equals 1 which had algebraic multiplicity 1 in this case, it is also getting geometric multiplicity 1. Okay. And you can quickly see what the eigenvector is going to be. The basis itself is just 1 0 0. So, if you are looking to collect linearly independent eigenvectors, 1 0 0 is already there. Okay. So, this is the first case. What happens when lambda is 2? When lambda is 2, things become slightly different. So, notice how things go slightly different from the diagonal case in this case. So, we do a minus 2I, you are going to get 1 minus 1, 0 and 1 on the diagonal, and the off diagonals remain the same. Okay. So, if you stare at it for a while, you see rank is 2. Okay. So, you can see rank is 2, there are two values here 1 0 0 1. So, this rank is 2, nullity becomes 1 and geometric multiplicity becomes 1. Okay. But then how do you identify the basis vector? You have to solve, right. So, you have to put down this matrix times x1 x2 x3 equals 0. So, you will get x3 equals 0 and then you will get x1 equals x2, right. Those are the two equations. You can mentally solve it. If you want, you can write it down. This matrix times x1 x2 x3 equals 0, you will get very quickly x3 has to be 0 and then x1 has to be equal to x2, right, minus x1 plus x2 equals 0. So, that is x1 equals x2. So, for simplicity I have simply picked 1 1 0 here. So, you can pick even 2 2 0, 3.14, 3.140, any value you can pick here. I have picked 1 1 0 for simplicity. So, I have found a basis for my null space for a minus 2I. Definitely geometric multiplicity is 1, arithmetic multiplicity is 1, but this 1 1 0 is already a slightly different vector from what we had in the diagonal case. So, notice how this becomes an eigenvector in this case. What happens when lambda is 3? Something more interesting happens when you do lambda equals 3. A minus 3I is minus 2 minus 1 0 on the diagonal, 1 1 here and remaining things remain the same. Once again rank is 2, nullity is 1, geometric multiplicity is 1, that is easy enough to see, there is no problem here. But then finding the eigenvector is slightly more involved and it turns out to be 1 2 2. Okay. Once again you have to solve it by write this times x1 x2 x3 is 0, you will get x2 equals x3 and then x2 equals 2 x1. Do you see that? Just mentally did that, but you can write it down if you like. X2 equals x3 and x2 equals 2 x1. Okay. So, you put x1 equals 1, so you got 2 here and this, or the x2 and x3 have to be 2. So, I picked 1 2 2. You can also pick any other vector here, but it will be a multiple of 1 2 2. So, 1 2 2 is the vector that is interesting. Okay. So, you can quickly see these three guys are linearly independent. Okay. Can you see? So, you can add it to the set. Why? Because this has got 1 0 0, 1 1 0, 1 2 2. It has got the triangular form, right, 1 1 2, the triangular form is there. So, it's linearly independent, it's already in some sort of a row reduced form. So, you can see that it's linearly independent. Okay. So, hopefully I have convinced you. The moment you go off diagonal, some interesting things happen. You are not going to get the canonical basis vectors as eigenvectors. Eigenvectors become interesting, you have to write down and solve it, but at least in this particular case some good things happen. Every eigenvalue, whatever algebraic multiplicity it had, the same geometric multiplicity also we got. Okay. All of them had algebraic multiplicity 1. So, you got geometric multiplicity 1. Okay. So, that is something important. Now, remember the value of lambda is such that a minus lambda I is singular. So, you will definitely find one eigenvector, right. One eigenvector has to exist because lambda a minus lambda I is singular. So, you should be able to find at least one vector in the null space. Will you find more than one is the interesting question, right. So, that is where we will see in the next examples, you will get some very interesting differences. Okay. So, here is the next example. Okay. Notice it is similar to last time, except the diagonal has now become 1 1 3. It was 1 2 3 earlier, it has become 1 1 3. So, notice what happens now. First thing is lambda equals 1 has an algebraic multiplicity of 2, right. I have not noted it here, but you can see lambda equals 1 has algebraic multiplicity 2. Lambda equals 3 has algebraic multiplicity 1. Okay. So, anyway, lambda equals 1, when you do a minus I, you have got 0 0 on the diagonal and then 2 here, and then the off diagonals remain the same, but interestingly rank is 2, nullity is 1, and even though algebraic multiplicity was 2, geometric multiplicity became 1 here. Okay. You are not going to find 2 vectors in the basis of the null space of a minus phi, a minus I, you are going to find only 1. Okay. Even though algebraic multiplicity was 2, you are getting only a geometric multiplicity of 1. Okay. So, these are interesting cases. Okay. So, notice why that happened, because of the off diagonal elements, right. If the off diagonal elements were not there, in fact, we will look closely, there are some situations where you may still get, but when because of the off diagonal elements, rank became 2 when you looked at a minus I, and once rank became 2, nullity becomes 1, and you will get only one geometric multiplicity. Okay. And what is that? That is easy to find. So, if you do a times x1 x2 x3 is 0, you get x1 being arbitrary. So, that is just the canonical basis vector E1. So, you have got you can start collecting 1 0 0 into the linearly independent eigenvector set. For lambda equals 3, things are a little bit more typical, but you have to do some work here. So, notice because of the off diagonal elements, when you do minus 3, you are going to get minus 2 0 here. So, notice here rank is 2, nullity is 1. So, AM is 1, algebraic multiplicity is 1, GM with geometric multiplicity is also 1. In this case seems okay, you are a little happy, you got same as AM and GM. And how do you find a basis vector here? Once again, you have to write down x1 x2 x3 equal to 0, you will get x3 equals 2 x2 and x2 equals 2 x1. So, you put 1 for x1, you become 1 2 4. Okay. So, it is a very typical simple sort of calculation. I have not shown the detail here, you get 1 2 4, these two are linearly independent, but interestingly this is the first time we are seeing a matrix which does not give you 3 linearly independent eigenvectors. Okay. So far every example we saw, we always got, for the 3 by 3 example we always got 3 independent eigenvectors. So, now there is a case where you have only 2 linearly independent eigenvectors, there are no other eigenvectors, right. If you are insisting on linear independence, you are not going to get any other eigenvector. So, these kind of cases are interesting. So, there can be matrices which will not give you, if it is n by n linearly independent eigenvectors, you may have something lesser. Okay. So, because of how the rank and nullity for a minus lambda I work out. Okay. So, we will see a bunch of examples, we will keep seeing a bunch of examples. Okay. Diagonal example again, 2 2 2 on the diagonal, when you had zeros on either side, a minus 2I became all 0, algebraic multiplicity is 3, and rank is 0 for a minus 2I, nullity is 3. So, you got 3 eigenvectors 1 0 0 0 1 0 0 0 1. Okay, geometric multiplicity became 3. So, this example we have seen earlier, it is a simple diagonal case. Now, I am going to complicate it by making it triangular. I will make it triangular by putting a 1 here, just a 1 here. Notice what happens when I put a 1 here. A minus 2I becomes this matrix, but it has got a 1 here. So, once it has a 1 there, so once again remember, even in this matrix the algebraic multiplicity for lambda equals 2 is 3. Okay, algebraic multiplicity has not changed. When I went from this matrix to this matrix, that is an important thing to highlight. I did not highlight it significantly enough, I want to reiterate it. When I went from this matrix to this matrix, even though I added this 1 here, it is still upper triangular. When I do a minus lambda I am going to get 2 minus lambda into 2 minus lambda into 2 minus lambda equals 0 as the determinant. Characteristic polynomial remains the same for these two guys, and algebraic multiplicity for the lambda equals 2 is still 3. But when you look at a minus 2I, the rank has become 1. The previous case we had rank 0, now rank has become 1, there is this 1 floating around here in the off diagonal. So, nullity becomes 2 and you will get only 2 linearly independent eigenvectors. Geometric multiplicity goes down to 2. Okay, you have got 1 0 0 0 1 0, you will not have 2. Okay, so, you see how that works out. The non-diagonal elements give you some difference between the arithmetic multiplicity and geometric multiplicity. In fact, you can push it a little further. So, you can make it 1 1 here on the off diagonal, then what happens? Again, once again the characteristic polynomial is exactly the same, algebraic multiplicity for the eigenvalue 2 is exactly the same, right. All of that is the same 3, but then a minus 2I has got rank 2 and nullity 1 because of the 1 here that I had here. So, you will have only one linearly independent eigenvector 1 0 0, okay. Geometric multiplicity becomes 1, okay. Geometric multiplicity cannot go below 1, okay. Why? Because I mean the way lambda is defined, a minus lambda I has to be singular, there has to be at least one non-zero eigenvector, okay. So, that is how eigenvalues are defined. So, geometric multiplicity will be at least 1 all the time, but it may not always be equal to the algebraic multiplicity. That depends on how the other values in the matrix work out, how the values in the matrix work out. It is a little complicated to figure out, okay. So, hopefully these examples are already giving you an idea about what can happen when you go to non-diagonal elements. Even with simple non-diagonal elements, I am not changing too many values, here there I am changing values, and interesting things can happen, okay. So, let us push these examples a little further just to get you comfortable with thinking about how the AM and GM are working with respect to different eigenvalues. I am going to give a few more examples and drive home the point with how this will work, okay. So, let us once again begin with a diagonal example. We have got 1 1 1 2 2 2, okay. There are 6 eigenvalues, but 1 repeats 3 times, 2 repeats 3 times, algebraic multiplicity 3 for 1 and 2, okay. Now, what are the eigenvectors? It is very easy to see. If you do a minus I, this is you are going to get 0 0 0. So, E1, E2, E3 are the eigenvectors for lambda equals 1. So, you have got geometric multiplicity 3 here. For lambda equals 2, you have got E4, E5, E6, the canonical basis vectors, and then geometric multiplicity also becomes 3. So, hopefully this diagonal case, we have seen it before, it is very simple. You notice here AM equals GM in the diagonal case. Now, I am going to look at all sorts of changes to the situation by adding non-diagonal elements and see what happens. So, here is what I am doing. I am adding 1 here. So, notice I have added this 1 here, this guy I have added here. So, what is this going to do? If you think about it, write it down very carefully, you will see that for lambda equals 1, you suddenly will not get 3 eigenvectors, you will get only 2. So, when you go lambda equals 1, this 1 is here. So, these 2 will become 0. So, you will have E1 and E2 as eigenvectors, nothing more will come out for lambda equals 1. So, geometric multiplicity becomes 2. And for 2 it remains the same. For 2 you will have E4, E5, E6, geometric multiplicity remains the same. There is no problem with 2. Now, I can add more guys. If I make this also 1, notice what happens here. When I put 1 1 here, for lambda equals 1, I have got geometric multiplicity of only 1. Okay, so only E1 is an eigenvector. These two guys will go away. Okay. Now, I can add even more, and if I add 1 here, okay, so okay, I have added 1 on the 2 side and kept the 1 part alone. So, now if I add 1 here, what is going to happen? E1, E2, E3 is going to continue to be eigenvectors for 1. So, geometric multiplicity becomes 3 again for 1, but unfortunately for lambda equals 2, you are going to reduce geometric multiplicity, you are going to get only 2 as geometric multiplicity. And then further one more 1 if I add, it is going to become only E4, E5 and E6 will not come. Geometric multiplicity can go down to 1 in these cases. So, you can add even more. I can add 1 1 here and then start adding 1 here. When I add a 1 here, what happens? Geometric multiplicity for lambda equals 1 also goes down. Okay, for lambda equals 2, I have already made it 1. Lambda equals 1 also, it goes down further by 1. And in fact, I can add one more 1 and make it E1. Okay. Now, the geometric multiplicities cannot go below this. Okay, there is no more room here. 1 has to be always there, you can't go below 1. So, notice how when you add the off diagonal elements, you do not even have to add too many, you just have diagonal and then add in the immediate off diagonal 1 here somewhere, you can get a wide range of geometric multiplicities without affecting the algebraic multiplicity. The algebraic multiplicity remains 3 throughout, right, because I am adding on the upper triangular part 1 anywhere. So, the algebraic multiplicity remains exactly the same, nothing happens there, but the geometric multiplicity starts changing. So, it is in your hands, you can keep changing it by changing the matrix A. Okay. So, hopefully this gave you a little bit more intuition, we will make it a little bit more formal and generalized soon enough, but this intuition is very important, and quite often when you want to play around with arithmetic multiplicity, geometric multiplicity, you can hook up examples with triangular cases like the way I showed you. In fact, this kind of a form has a special name, it is a canonical form, that is why I am giving you these examples. These examples are supposed to be as general as possible. Any situation you want, you can simulate with these examples. Okay. So, let us look at one more case here. Okay, so here is one more case, slightly more generic. I am showing you just to repeatedly iterate. Quite often people forget these simple examples and get confused about algebraic multiplicity, geometric multiplicity, eigenvalue, eigenvector. These examples are meant to just illuminate those ideas. Okay, so let us go to a slightly more complicated example. Once again triangular, but now I have 3 eigenvalues. Okay, so in the diagonal case, notice I have 3 eigenvalues 1, 2 and 3. One appears with AM1, algebraic multiplicity 1, 2 appears with multiplicity 3 and 3 appears with multiplicity 2. Okay, once again for the diagonal case everything is very clean, right. For lambda equals 1 you got E1 as an eigenvector giving you geometric multiplicity 1. For lambda equals 2 you have got 3 eigenvectors E2, E3, E4 giving you geometric multiplicity 3. For lambda equals 3 you have got only 2, you get E5 and E6. Okay. Now notice what I am doing, I put a 1 here. Okay, I put a 1 above this third 2 here. Notice what happens, lambda equals 1 nothing happens, lambda equals 3 nothing happens, but lambda equals 2 suddenly you lost the E4, E4 is gone, you will get only E2, E3, geometric multiplicity goes down. Now I add one more, geometric multiplicity for 2 goes down further, it becomes only 1. Okay. So now I can go further here on 3 and add one more for 3 also geometric multiplicity goes down, E5. Okay. So if you notice I have not added 1 in these parts, in this 0 and this 0 I have not added 1. If you can add 1 there, it just makes it a little bit more complicated. You will see that the canonical basis vectors may not be eigenvectors anymore, you will have to do some changes here there. It is not too complicated, I will urge you to try it, and once again you can try that and post on discourse what eigenvectors you got. You will see that you can play around with this and change the eigenvectors also. Okay. So just to show you that these off diagonal values, when you add them, the eigenvectors number of them changes, the geometric multiplicity changes. Okay. So I hope this is convincing to you. All these examples, go through them once again, make sure you understood how the eigenvector calculation works. Okay. So now let us generalize. Okay. So I am going to look at an arbitrary n cross n triangular matrix. I have picked upper triangular here, you can also pick lower triangular, everything goes exactly the same for upper or lower, I am not distinguishing between the two. So you have got A11 to ANN on the diagonal. Off diagonal I have just put a star to indicate that these could be non-zero. Okay. So what happens to the algebraic side of things? If you look at the characteristic polynomial determinant A minus lambda I, it is going to factor as, let us say, lambda minus lambda 1 power A1, lambda minus lambda 2 power A2, lambda minus lambda r power A2. Basically I am saying these diagonal values are lambda 1 repeated A1 times, lambda 2 repeated A2 times, so on till lambda r repeated AR times, just to count the multiplicity. So you have got r distinct eigenvalues with corresponding algebraic multiplicities A1 to AR. Just to rewrite it, it starts from lambda 1 lambda r. Once again A1 plus A2 till AR has to be equal to n, right. So that is also true. So this is just the general picture for how an arbitrary triangular matrix will look. Now how do I think of geometric multiplicities? So let us write down. For the eigenvectors, if you pick lambda equals lambda 1, what is going to happen? A minus lambda 1 I, it is going to look like this. Okay. So you are going to have 0 for the first A1 columns on the diagonal, but then I do not know what is going to happen to the off diagonal. Likewise, these guys are non-zero, but there are values above it also. Okay. So this is a little confusing. So let us look at it closely. On the diagonals, lambda 2 minus lambda 1 to lambda r minus lambda 1 are definitely non-zero. Why? Because these lambda 1 to lambda r are distinct values. The first A1 diagonal values are 0, but above those diagonal values you may have non-zero values. So I do not know how this is going to work. Okay. So if all of these guys are 0, this entire A1 to A1 will become 0, and then you will have a proper geometric multiplicity also being A1. Okay. But some of these things could be non-zero, which is what happened there, right. So even if one value is non-zero, rank goes down. Okay. So this is how one needs to study this carefully. So if you look at it very closely, rank of A minus lambda 1 I has to be less than n, that is for sure, because the first column is all 0. Okay. First column is all 0 anyway, I mean this is how it has to be less than n, it has to be singular, right. A minus lambda 1 I has to be singular, first column is non-zero, so it is less than n. But because these guys are non-zero, these diagonal values are non-zero, rank of A minus lambda 1 I is also greater than or equal to A2 plus A3 till AR. How many of these values are there? Lambda 2 appears A2 times, lambda 3 appears A3 times, so on, right. So how many of them are there? A2 plus A3 till AR, and that is also equal to n minus A1. right? A2 plus A3 till AR is also n minus A1. Okay. So, rank of A minus lambda 1I, why am I obsessing about the rank? Because that gives me the nullity and that tells me the geometric multiplicity. I am trying to go towards geometric multiplicity. Okay. So, rank of A minus lambda 1I, while it has to be less than n, just by the definition of the eigenvalue, it has to be less than n, because A minus lambda I is singular, right? It has to be less than n. We are also seeing the rank of A minus lambda 1I in the triangular case. Okay. In the triangular case, I make this argument that it has to be greater than or equal to n minus A1. Okay. So, what does this mean? Nullity of A minus lambda 1I is at least 1, okay, that comes from this part here, the top equation, and nullity of A minus lambda 1I is at most A1, it comes from the second inequality. So, rank is less than n, which means geometric multiplicity or nullity of A minus lambda 1I is greater than or equal to 1. Okay. On the other side, rank is at least n minus A1, which means nullity can be at most A1. So, what we have shown for a triangular matrix right now, we will generalize it later, is this very simple and important property, the geometric multiplicity lies between 1 and the algebraic multiplicity. Okay. So, this is a fact which holds for all matrices. I have proved it only for the triangular matrix here. Later on, we will prove it for the general case. It holds true for all matrices that whatever algebraic multiplicity you have, your geometric multiplicity has to lie between 1 and the algebraic multiplicity. It cannot take any other value outside of it. Okay. So, it is an important result. So, finally, putting all these things together, the eigenvalue lambda equals lambda 1 to lambda equals lambda r, each of them can have possible geometric multiplicities 1 to A1, 1 to A2, 1 to AR. Okay. So, it cannot exceed A1 here for lambda 1, it will be at least 1, but it can take any value between 1 and A1. We saw how to adjust the off diagonal values to give you any of those values, right. So, that is something that you can do. It can be any value from 1 to A1, it can be any value from 1 to A2, of course integer values, and then 1 to AR, okay, and 1 less than or equal to GM less than or equal to AM for every eigenvalue. In this particular case, we have proven it. So, in general, this is also true. Okay. So, previously I showed it only in the triangular case, but even if you take a general matrix, you define the general characteristic polynomial, factor it using a computer, find the multiplicities, algebraic multiplicities and write it down. Guess what? The geometric multiplicities are between 1 and the corresponding algebraic multiplicities. Okay. So, we have to prove it, and this will be proved in a later lecture. Okay. Hopefully, these ideas have crystallized for you. They showed you a bunch of examples and then showed how that goes, but I have shown only for the triangular case, right. So, let us take a few non-triangular cases and see how all this works out. In the non-triangular case, you have to do a little bit more work to find the eigenvectors. It is not possible to find them directly. So, what we will do is we will take a few non-triangular matrices and go through the motions of finding eigenvectors and see how that works. That we will do in the next lecture. Thank you very much.